Hey everyone, welcome to the Foundry by Forge College. I'm super excited to have you here for today's explainer on what is C-level execution. Now, if you're jumping into this right after wrapping up the capstone, deploy and optimize on Solana mainnet lesson, well, huge congratulations are definitely in order. You did it. You've successfully pushed your code to the mainnet, your monitoring is all set up, and you've got your rollback plans ready to go. That's a massive milestone. But, it kind of begs the question, what actually happens next?
Right? Your code is live. Now what? It's honestly a fantastic feeling, right up until that terrifying little thought creeps in. What exactly is going to happen when 10,000 users try to smash the buy button on your brand new program at the exact same millisecond? Like, how does the network even process all of that without the servers literally bursting into flames? How on earth does it keep all that chaos organized?
Well, here is our agenda. To understand how your program survives that massive concurrent load, 1. Meet C-level runtime. 2. The stage manager. 3. Three pillars. 4. Parallel versus serial. And 5. Scaling programs.
Okay, let's jump right into section 1, meet the C-level runtime. So C-level execution is Solana's parallel runtime and deterministic scheduler. You can really think of it as the ultimate traffic controller, layered right there between the incoming transaction queue and the low-level execution engine. Its one and only job is to make extremely safe, lightning-fast concurrency choices. It absolutely has to preserve the correctness of your program, even under totally overwhelming load. It essentially takes this massive wall of simultaneous requests and logically organizes them so the execution engine can just do its thing without corrupting a single byte of data.
Moving on to section 2, the stage manager metaphor. To really visualize this, I want you to imagine a highly ambitious, maybe slightly chaotic theater production. In this metaphor, the transactions your users are constantly submitting, those are the individual scenes of a play. The Solana accounts that your program interacts with, those are the physical stage props. And Sealevel itself is the incredibly efficient, but probably highly stressed stage manager. This stage manager looks at all the props that each upcoming scene is going to need and quickly decides which scenes can actually happen on the stage at the exact same time without the actors, getting into a fist fight over a single prop. And this is a great way to illustrate the separation between what a user wants to happen and how the network actually handles it behind the scenes. We call this transaction intent versus execution order. The transaction intent is basically the scripted scene, right? It's the user signing a transaction saying, hey, I want to execute this code using these specific props. But the execution order is when and where our stage manager actually allows that scene to run on the stage. What a user signs for isn't always the exact millisecond it runs. The user's intent is a totally separate thing from C-level's scheduling reality. Now, to keep everything perfectly safe during the performance, C-level relies on something called an execution context. This is a logical boundary that provides complete state-level isolation. So going back to our theater for a second, this context ensures that the actors in a specific scene have a totally isolated, consistent view of their props. They're not going to accidentally grab a half-painted prop or see partially updated state from some completely different scene going on across the stage. The context keeps the reality 100% consistent.
All right, section 3, three pillars of C-level.
Let's look under the hood. C-level's brain basically operates on 3 tightly coupled duties or pillars. The first pillar is analysis. C-level inspects every single transaction and extracts a list of all the accounts it's going to read from or write to. It's basically building this giant access graph. The second pillar is scheduling. It takes that graph to find groups of disjoint transactions, meaning transactions that touch completely different accounts, so they can be scheduled to run in parallel. And the third pillar is enforcement. Look, where conflicts do exist, C-level steps in and applies locks to prevent data races, which means, some things will just have to patiently wait their turn.
Section 4, parallel versus serial execution. Let's see this in action. Imagine 3 transactions hit the network at pretty much the same time. In step 1, we've got transaction 1, which is a token transfer between Alice and Bob. We also have transaction 2, which is an order book update using an oracle. Because these 2 transactions touch completely different accounts, they're using different props, C-level fires them off in parallel, no problem. But then look at step 2. Transaction 3 is a transfer between Alice and Charlie. Notice the overlap there. Transaction 3 needs the Alice account, which transaction 1 is actively using. So the stage manager immediately steps in and forces a lock, and transaction 3 is forced to wait. It gets serialized.
So the absolutely crucial takeaway here is data race avoidance. Anytime you have overlapping write sets, like 2 transactions trying to write to that same Alice account at the same time,
Sealevel is going to conservatively serialize the work. It forces sequential execution. Now, this is great because it guarantees your program's correctness, but it's bad because it causes noticeable latency for your users.
Which brings us to Section 5, scaling your Solana programs.
If you actually want to avoid these bottlenecks and scale your dApp effectively, you have to design specifically for Sealevel. First up, you need to reduce shared writable state. If every single transaction in your program touches one global configuration account, your entire program is going to bottleneck instantly. Second, partition your account data. Split ownership up so that transfers touch distinct escrow accounts, which maximizes your parallel throughput. And finally, monitor your queues for hot accounts. Those are the specific props everyone is fighting over, and finding them tells you exactly where you need to go in and optimize your code.
Look, if you remember nothing else, I want to leave you with this golden rule. Always declare all accounts a scene might read or write. You have to give Sealevel all the information up front. If you're relying on hidden global state, the stage manager literally can't do its job. But if Sealevel knows exactly what props your code needs before it even runs, it can schedule things safely, correctly, and unbelievably fast. So now you know how Sealevel handles scheduling, but honestly, it begs a much bigger question. When code is running this fast and concurrently, what exact lifecycle checkpoints keep the whole thing from just tearing itself apart? Like, how does a transaction physically flow through the runtime from start to finish? Well, we are going to tackle that exact journey in our next lesson as we continue our introduction to Sealevel execution. To dive deeper into that lifecycle and to check out way more of our advanced Web3 learning programs, be sure to visit forge.college. Thank you so much for watching this explainer by Forge College. Keep on building, and I will see you in the next one.